Dear students, now let's understand one question. So this is a case of swaying. Okay, so how does the swaying happen? So here swaying is happening. You can see there is leg AB and CD. They are not at same level, and the horizontal direction force is acting here 30 kilonewton, and there is also UDL acting over here. So by looking at this case, this is a case of swaying. Now the question is, analyze the portal frame shown using stiffness method and draw bending moment diagram and deflected shape. Okay, so as you have seen in previous, I have given introduction about the step by step how do we proceed for this particular problem. So let's see step number one. We have to find out what are the degree of freedom. Okay, so degree of freedom for this particular case. Now you can see that the end A and end D, it is fixed, right? There is a swaying case. Okay, means swaying means what? This can, this can tilt in one direction. So if this can tilt like this. So where is the degree of freedom? So there will be rotation at B, there will be rotation at C, and there is as well swaying. So the condition says the swaying amount is same. Okay, so if we say rotation theta B at B point, theta C at C point, and this delta, whatever the swaying, that value is same. Okay, so it's like this. So if these are two members, so this value, okay, so this swaying, this amount, okay, this is delta for this particular frame. Okay, and this is C. So that's why our dk is theta b, theta c, delta. Okay, so three unknowns are there. Now step number two, that we have to assign coordinates. So theta b, theta c, and delta. So we can say it as 1, 2, 3. Okay, so let us call here, this is point number 1, coordinate of number 1, this is 2, and the whatever swaying is happening, that will be 3. So we can assign like this, this is 1, this is 2, this is 3, because we have to form stiffness matrix, right? So there we have to remember this. Now let us consider theta b. Okay, let us apply the first unknown here, unit rotation. Let us apply unit rotation at point B. Okay, now when some rotation is acting here, okay, when some rotation is acting here, so how do you draw this? How you will draw this curves. So let us see, at point B there is this rotation acting. So what is happening? Just see, when this is going like this, okay, what is happening? It is trying to push it down, and it is trying to push it down. So we can draw a curve like this, and when it is moving like this, it is coming here, so it is pushing outside. So the other curve will be like this. Okay. So whenever initially, okay, this part, the first part, this value is always 4 ei by L, and the end part, the tail part, it is always half of the moment, 2 ei by L. Okay, so that way I have written all these values. So here it is 4 ei by L for this curve, here it is at the other end, the far end moment. Okay, because of the unit rotation, here the moment is 4 ei by L, and the far end moment is half of it, 2 ei by L. Similarly for this also it is 4 ei by L, and the other end moment should be 2 ei by L, but this is a fixed end, so it becomes 0 over here. Okay, now here also simultaneously let us understand one more concept. So here you see that it's a clockwise rotation, right? If we see, it is a clockwise rotation. So when we try to understand the reaction part of it, okay, so in this case there will be reaction to balance this part. Okay, because it is a clockwise rotation, so to balance it there has to be a anti-clockwise balancing. So there are these reactions, and its standard value is 6 ei by L square. Okay, 6 ei by L square. So remember this. But now because it's a fixed end, so this part becoming 0 over here for this particular case only. Okay, so remember this, because we have a swaying, so this may be of our use. So let's see. Now Yeah, I was trying to say the, if rotation is clockwise, then the reaction should be such that it should balance the member. So it should be anti-clockwise. So here reaction is clockwise, right? Reaction is clockwise. So uh, the rotation is clockwise. So the reaction is anti-clockwise. Now let us write down coefficient, stiffness coefficient. So K11, okay, K11. Now we have given the name. So what is our point? Theta B. This is a B point, okay. So this is A, this is B, this is C. So this is first coordinate, this is second coordinate, and the third coordinate with respect to swaying. So K11. So because of unit rotation at 1, what is happening at one place? What are those moments getting created? So you can see that because of unit rotation, there are two values, 4EI by L, 4EI by L. Okay, so when it is about rotation, we are just seeing the rotation value. Don't get confused with this reaction. That will come in a case when there is a any deflection is there. Okay, that time we'll consider. So this is 4EI by L, 4EI by L. And now here you have to be very careful about L. So when I say this 4EI by L, it is respect to this particular length, and this length is 5 meter. Okay, so 4EI by L here, 4EI by 5, and in this case 4EI by L is, this is 4 meter. So we have taken 4EI by L is 4 meter. So when you add them up, you get answer 1.8 EI. Okay, now let's take the second case, K12. So because of unit rotation or unit force at 1, what is happening at 2? There is only one moment. So write down 2EI by L. Okay, 2EI by L. So we have written here. Now the third case, because of unit force at 1, what is happening at third direction, and what is third direction? So I have just drawn here third direction, right? This is our third direction. So what is happening? So there is a tendency that it is swaying like this in this direction, and the reaction what we have written is 6CI by L square, right? 6CI by L square. So if you see, this is in negative direction, right? Left side. So left side direction we consider as negative. So minus 6CI by L square. Now here again it's very important. This L will be in with respect to what? So whenever there is some deflection like this, okay. So this is with respect to this leg, right? So that's why we have to be careful and take only this length, okay. So here for this particular K13, we have taken L is 5 square. Okay, so our answer is minus 0.24 EI. Now let us consider the second case. Apply rotation at C. Okay, you may also write apply unit force at C. So the standard wording. Okay, so when you apply unit rotation at C, now how the shape will be. So just see that this particular unit rotation, this is trying to push it here in this direction. So this will be the shape of the curve. Further, when you go upside, it is trying to push it upward. So this will be the shape. Now again write the usual way of writing moment, 4EI by L. The far end will be 2EI by L. Again here 4EI by L. In this case this is L, right? So this is 3 meter. For this case it is 4 meter. This is 4 meter by L. L I am talking about. Now the reaction, if you see, it is in clockwise direction. So to resist that, there has to be an anti-clockwise direction reaction. So here 6EI by L square. Okay, 6EI by L square. So L is 3 meters. So that we have written here. Okay, so and here it is a fixity, so we are showing it as 0. Now let's write down all the coordinates here, coefficients here. So K21. Now because of the unit rotation at 2, what is happening at one place? So it is 2EI by L, 0.5 EI. K22, because of unit rotation at 2, what is happening here? So write down those coordinates, those values, 4EI by 4 and 4EI by 3. Okay, so we get this value. Then K23, okay. So because of 2, what is happening at swaying side? So that is this reaction, right? 6EI by L square. So that is in negative direction. Why it is negative? It's in moving in this direction, and the swaying assumed as in right direction. So this is minus 0.67 EI. Now let us consider the third case. Apply unit displacement at B and C. Okay. So here basically, as I said, that whatever displacement is happening, that is equal, right? So we have applied like this unit displacement. Now students, here also you have to understand this is one more concept here. So whenever there is some displacement happening, okay, whenever some displacement happening, so say like this, okay. So because of this unit displacement, there is some moment gets created, and this moment is equal to 2ei by L square, okay, 2ei by L square. So you can see that when you consider the rotation, you know, the rotation, because of rotation what moment gets created is 4ei by L, we have seen. But whenever there is a displacement, because of some displacement, the moment gets created as 6ei by L square. The standard way of writing is 6ei by L square, and here also 6ei by L square. Okay. Now this is in anti-clockwise direction. So to resist that, there has to be a reaction, and this reaction, it is 12ei by L cube. Okay. So remember this. This is important formulation. Okay, so this is what we have drawn here. Because of fixity, we have made it 0. Okay, so same applies for both the case, and L is always the length of vertical member, right? Those are getting displaced. Okay, those. So that's why those lengths we have to take. Now coming to L31. So because of displacement, what is happening at one place here? You can see at one place there is a moment created because of 3 1, you know, one direction. What was there originally? Rotation. So that is minus 6 ei by L square. Okay, so substitute values and get the answer. Now because of 3, what is happening at 2? 6 ei by L square. Okay, so we have to calculate, and the answer for 3 2 is minus 0.67. Okay, this will be in ei. There is some, I think, writing error. Okay, I think this is the correct form. Okay, we have written here. So here K33, because of 3, what is happening at third direction, and third direction is of swaying. So 12 ei by L cube. So this plus this, you will add both of them. Okay, and the value is 0.54 ei. So once you have done this, the corrected stiffness matrix. Okay, so corrected stiffness matrix, you get it like this. So you may just recalculate and check it if it is correctly done. So there might be, you know, some let me just check with this first 3 1 value. I think some writing 6 divided by 25.24. Yeah, here there is some error in writing. So this is minus 0.24, and then this is correct. Okay, now it's done. Okay, so once you get the stiffness matrix, okay, final stiffness matrix, so this is our step number 4. Now calculate fixed strain moments. Okay, so you know the fixed strain moments. How do we calculate? Now MF of AB, there is a UDL acting and there is a point load. Okay, so for that you use the standard formula. You must be having our standard table how to calculate fixed strain moments and get the value. Okay, so AB and BA, so I will not spend much time here. You know how to calculate fixed strain moments. So BA value is this and BC value is this. Okay, so use WL square by 12. So when you use the standard formulas, you will get fixed strain moments, and CD and DC, there is no load acting, so it is 0. Okay, now let's move to the next step. Now step number 6 is to calculate P matrix. Okay, so to calculate P matrix, we have to consider vertical members. Okay, vertical members and all loads, whatever loads are acting, we have to consider that, and even the moments. Okay, fixed strain moments, whatever acting, that also we have to consider. Now we have considered R1 and R2. We have considered R1 and R2. Those are the reactions at B and C. Okay, we are just considering vertical members. So whatever unknowns are there, okay, so that we have to see. And those vertical, those P1, P2, P3, okay, these three terms we have taken which are corresponding to theta A, theta B and delta. Okay, so because of this rotation at A and B, okay, as there is a error in writing here, this is corresponding to theta B, theta C and delta, okay, at point B, C and the delta. So that is what we are going to see here. So P1 is corresponding to theta B, with some rotation we have applied here, right? Now let us see P1. What is P1? So for this particular point P1, we have to add fixed end moment at MF of BA and MF of BC, okay? So here if you see, A, B, C, D. Okay. So MF of BA plus MF of BC. This is our first coordinate, right? So P1 is equal to MF of BA plus MF of BC. Now we have the values. Simply substitute and get the answer. Then at P2, P2 is MF of CB and MF of CD. Fixed end moment at CD. So 40 and here the other end it is 0. So our final answer at P2 is 40. Now P3. For P3, when there is some swaying, right? There is some swaying. We don't have what is the resistance mechanism there, right? Because of that swaying, there are some reactions coming in the picture. So for P3, let us consider some reactions R1 and R2. Okay, R1 and R2 we are considering. In this case, this is R2. Okay. So let us consider such free body diagram. Now what we are going to do, we are going to calculate R1. Okay. So for R1, how you will calculate that reaction? Okay. What is the reaction getting to resist that swaying? Okay. What is that reaction getting created? So here consider moment about A point to calculate, because we have to calculate R1. Consider moment about A. So minus 60, minus 60.41. This is anti-clockwise. And this is plus 60.41. This is clockwise. Then there is a load 30 into 2.5 and clockwise. So 30 into 2.5. Then there is a UDL. So 20 into 5 into it will act, CG will act here, right? 5 by 2. Then this moment considered, and then R1 into 5. It is anti-clockwise. It is making anti-clockwise rotation. So our R1 is 65. Okay, R1 value is 65. Now let us calculate R2. So for R2, you see there is absolutely no load acting. So R2 will become 0. Now our P3 formula is R1, which is in negative direction, and R2 which is in positive direction. So P3 is coming as minus 65. Okay, minus 65 value we are getting for P3. Now we have to write it in matrix form. But before going to the next step, remember that we have to change the sign. Okay, we have to change the sign here. Note the sign of P, change the sign of P before using it in step number 7. So we have to now write down the matrix, K matrix, and this theta matrix equals to P matrix. Okay, so we have to change the sign of P. So K matrix I have copied here, theta B, theta C, delta, and the P matrix with the change sign. Now you solve these equations. Okay, you can solve directly the matrix in your calculator and get the answer. So theta B, theta C and delta answer, these are the values. Okay, after calculation I am getting these values. Once you get these values, now calculate final moments. Okay, so again, you know slope deflection method, you are good at it, but here you have to be careful. Now when you calculate final moment, okay, so moment at AB, so this is our member AB. So here this member AB is going under sway, right? It is going under sway, so there is delta. So this delta you will consider here. Okay, theta A, anyway it is fixed end, so theta is 0. Theta B, there is some value for theta B, we have it, and delta value also you have to consider, and you have to be very careful about the signs. Okay, sign what we have taken is negative and positive, that you have to be careful, take it properly. Okay, so we are getting theta B as negative and other two values are positive. So substitute and get the answer for M of AB. Similarly for BA also, this delta will come in picture, theta A will become negative, theta A will become 0, theta B value you substitute, you are getting M of BA. Now in M of BC, M of BC is a vertical member, right? So it is not coming in the picture of swaying, right? So that's why the delta is becoming 0 here. Okay, delta we are not considering here in this case, because the swaying is happening with the vertical member, not the horizontal member. So this is 0. Theta B and theta C, substitute those respective values. So I am getting M of BC is minus 37.634. Now consider M of CB, the same thing. Again substitute values and get the answer. M of CD. Now in CD again delta will come in picture. Okay, and you have to be careful about the length you are taking. For CD, member length is 3 meters. So substitute that. EI in this calculation, EI will get cancelled. Okay, so CD is this. And DC is, you are getting it as, we are getting it as 60.61. Okay, so now here we got the final moments. Now coming to the drawing of bending moment diagram. So students, write down all the bending moment values you got and draw the diagram with fully loaded structure. Okay, original loads whatever acting. So draw this diagram, show the fixed end moments acting over it. Now what is happening here, that we can draw the bending moment diagram with standard procedure. But if you see the member AB, there is a uniformly distributed load acting as well as a point load acting. So we cannot, directly draw bending moment diagram for this. Like for this UDL, you know that simply you draw a parabola, right? Considering simply supported beam, and even show the moment at the same point, right? Here you will show the moment and you can directly draw the bending moment diagram. But for member AB, there is little bit difficulty in directly drawing the bending moment diagram. So what we are going to do, we will draw AB as a free separate member, calculate reactions at these points, okay, and calculate moment, what is the maximum moment at this point. Okay, this is a midpoint, so let us consider this as a point E. Okay, so this particular member I have drawn it here. Now we have to calculate maximum bending moment E, but before that we need to find out horizontal reactions. Now because this member is vertical, so these reactions will be horizontal. So let us calculate HI and HB with the standard procedures. So summation of forces in x direction, if you do, you get HI plus HB is equal to 130 kilonewton, because 30 kilonewton load is there, and this 20 kilonewton UDL, right? So 20 into 5, so 130 kilonewton. Now consider moment about B, because our interest is to find out HA. We have to find out a moment at E, right? So HA is moment about B when you do. So HA into 5, moment about B point. So HA into 5 plus this moment will come, and the whole UDL will come 20 into 5 into 5 by 2. So this is clockwise direction, but this is anti-clockwise. This is also anti-clockwise. That's why here it is negative values. And even this moment is anti-clockwise, so negative value. So with this you get HA and HB 65 kilonewton. Now finally when you get reaction, calculate moment about E point. So moment about E point. So just consider this load, forget the rest of it. So 65, HA is 65, right? Here we got 65. So 65 into 2.5, then this moment will come 2.332, then minus 20 into 2.5 into 2.5 by 2. So we are considering UDL in this area, right? Here it is 20 kilonewton meter. So because moment at E, so consider just this part. And then you are finally we are getting M is equal to 102.3 kilonewton meter. So once we get this, then let's draw a bending moment diagram. So in this bending moment diagram, just see, write down all the values. So first M of AB. So AB ka moment what we have is 2.3332, right? So let us consider 2.332. So just plot one point here. This is 2.332 AB, and BA is minus 2.764. Okay, so 2.332. So what we are going to do, we are going to draw this bending moment diagram at one side of it. Okay, because there are combination of loads. So for this case, let us draw all the bending moments. Let us plot all moment at one side only. So 2.332 here and 2.764 here we have plotted, and the maximum bending moment is 102.3. So what we will do, draw here straight line. So this is a straight line. Okay, from here to here it is a straight line. and then there is a UDL. So because of UDL there will be a parabola. So from here to here it is a curve, it is a parabola. Okay, so this is one part of the diagram. Then coming to the next part, BC. So for BC the final end moments are 37.634 and here 52.006. So draw those, join the line, and also draw a simply because of UDL you get parabola. Okay, so the two values, the standard way of drawing bending moment diagram, we have studied this in slope deflection method, right? So that way you draw. Now the remaining moments are, here it is 52 and here it is 60.61. Okay, so when you are coming to draw, so the tension side, okay, the negative side we are drawing it inside, and the positive here it is outside. So the values are 52 and 60.61. So the when you stand here, okay, mostly when you draw, yeah, one more important thing, that whenever you are drawing bending moment diagram, you just assume yourself that you are standing inside and then you are looking at all these directions. Okay, so when you are drawing, your see direction is like this, here your direction, seeing direction like this, and here also you are seeing direction like this. Okay, so when you see from here, so CD, when you say CD it is 52. Okay, 52 it is positive, so it is going like this. So we have drawn 52 like this. And when you see 60.61, okay, in this direction, so this is also positive, both the moments are clockwise only, so it is coming in this direction, right? So we have drawn it inside 60.61 and then draw the connect the lines. Okay, so this is our final bending moment diagram. So this is positive value, this is positive, the remaining parts are negative, and this is our bending moment diagram. Now the deflected shape is, because of swaying, naturally it will deflect like this, right? And this particular part, because there is some loading, right, and because of swaying it will go little down, because there is some load acting, so there will be slight, we have to show the deflected shape there, and then it is connecting this point. Okay, so this is our final deflected shape for the beam, for the particular frame. Okay, students, so I hope you understood, and if any doubt is there, you can ask me in the comment box. Okay, thank you for listening.